that integration by parts formula, says we get to take some kind of oh, sorry, slide that down so it's actually on the screen. We get to take some integral that we don't know how to work with and swap it out for something that we hope is better. One thing to keep in mind, integration by parts always trades one integration for two. Every single time you use integration by parts, you're swapping one integration for two integrations. Here's what I mean by that. Well, we'll do a problem and it'll come up. So the challenge with integration by parts really is to figure out, when I am looking at a problem, what's the part that I should call U and what's the part that I should call DV? And I'm here to let you know that 95% of the time, this will work. Thinking about the types of functions that you know how to take derivatives of. What is some type of function you know how to take derivatives of? Or we're supposed to know how to take derivatives of? Just thinking derivatives. People are whispering. So chain rule is a derivative technique, but I'm thinking x squared, absolutely. We should be able to take the derivative of something that looks like x's to powers. So I'm going to call that algebra. Stuff that looks like a number times x raised to a number. What's something else we should know how to take derivatives of? Yeah, totally. Anything else we should know how to take derivatives of? Totally. And I'm missing one letter here because we should know how to take the derivative of logs. I have written these in the order that they suck the most to integrate. And that is how I'm going to choose U. I'm going to find the part that would suck the most to integrate and make that equal to U. Let's get some examples going. But LATE is a convenient acronym, so that's why I've written in that order. So let's say I'm looking at something like x to the third times natural log of x dx. I'm going to make my quick check. I can't make it look like x is raised to powers. Does the derivative of one part equal the other part? No, the derivative of x cubed is x squared. Derivative of ln of x is 1 over x. Neither of those are hiding in there. So my only choice, because this is kind of a mixture of some of these things, is to do integration by parts. Well, I've got a mixture of algebra and logs. So I say to myself, who comes first in the word LATE? Logs. That's what I'm going to let U be equal to. And that means that whatever is left once I choose U has to be equal to dV. So dV has to be x cubed dx. Well, the integration by parts formula says that I'm going to swap this out for U times V minus the integral of V du, or what I like to remember as ultraviolet voodoo. So if I'm going to need to translate here, I have a U, but my formula requires me to get a du, which means I'm going to take a derivative. And my du is 1 over x dx. And my formula requires me to get a v, but right now I have a dv. And this is the part where I was saying integration by parts trades one integral for two. Because how do I get v? I have to find an antiderivative or do an integral. Our hope is that the thing we've chosen is pretty easy to find the antiderivative of. So x cubed, I'm going to add 1 to the exponent and divide by the new exponent. There are algebra reasons that I don't have to put the plus c right here. At this point, just believes that the algebra is going to work out and I don't have to put the plus c right there. It's going to come out in the wash. So now I'm going to plug things in and see where we get. Over here, I've got u, so that's going to be natural log of x, or ln of x, times v, x to the 4th over 4, minus the integral of v, which is x to the 4th over 4, times du, which is 1 over x dx. My recommendation whenever you're doing integration by parts is after you've plugged into the formula, pause, simplify, and then try to integrate. So I'm going to pause here, simplify whatever I can in that integration, and then move forward. So 1/4 x to the 4th ln of x. Over here, I can pull the 1/4 out in front. And then x to the 4th over x. Conveniently, one of those x's cancels out, and I'm just left with x to the 3rd. Now we can complete that second integration step. You could multiply the 4's together and call that a 16th if you wanted to, or you could just quit there. Question?
X, the story of the life points to the but why are we putting the X?
So I've got to integrate this again. What is the integral of x cubed? Yeah, every integration by parts problem forces me to integrate twice. We just hope that they're easier integrals to do, or at least integrals that we can do at all. And we can definitely see there are lots of ways to complicate problems. But we've got time to get a few more examples in the notes. So let's get a few more examples in the notes. Question before we do that? So every integration by parts problem, we're going to end up integrating to go from dv to v. And then we're going to end up integrating after we plug into the formula. So every single time. Yeah. Oh, well, you can multiply the 4's together. You call that x to the 4th over 16. Yeah. There isn't, no, you don't need to. And this would be fine. And also, there's not much else you can do. So yeah. I don't know how gross to get. Sometimes we get an integration by parts problem that we're actually going to have to integrate more than once, more than twice, several times. So let's do one where at least we're going to integrate a few times. And I'm going to do x squared e. I'm gonna make it a little bit gross. I'm gonna make it x squared e to the 3x. But we can handle it. I had a math teacher. I went to college in New Mexico, and I had a math teacher in college that used to say, "This isn't the Santa Fe School of Ballet. We can handle the algebra." So I hear his voice in my head every time. I'm like, "Oh, this is gonna be complicated algebra. We can handle it." Okay, so I'm walking up to this problem and I'm asking myself, hey, does the derivative of one part equal the other part? It really doesn't. So I'm going to have to do integration by parts, but let me pause for a second. Does the derivative of one part kind of equal the other part? That one's a U substitution. So just because we know how to do integration by parts doesn't mean that every problem should be integration by parts. So this one would be a U sub. This one requires integration by parts. So let's do the integration by parts problem. And I'm going to say, oh, I've got a mixture of algebra and exponentials. A comes first in the word late. I'm going to let U be equal to x squared, which means my dv is everything else, which is e to the 3x dx. My derivative is going to be 2x dx. And my antiderivative over here, it's almost e to the 3x. I just have to remember to divide by that 3. So I'm going to write that as 1/3 e to the 3x. Plugging that in to my ultraviolet voodoo formula. Are the colors helpful for anyone? Should I keep going with the colors? Okay. So, so my U is x squared. My V is 1/3 e to the 3x. Putting in my V here again, I've got 1/3 e to the 3x. And then my du was 2x dx. I said 2x and I wrote a d. I don't know, because it's Tuesday or something. Every time I get to this point, I pause and simplify. Yes.
The V was 1/3 chain.
Yeah, we're like undoing the chain rule. Totally. Yep. So I am looking at, if I clean this up a little bit, 1/3 x squared e to the 3x. I'm going to take the 1/3 and the 2 and pop them out in front. So I'll have minus 2/3 x e to the 3x dx. So I look at my remaining integral and I ask myself, hey, does the derivative of one part equal the other part? Sadly, no. So I'm going to have to integrate by parts again. I have a mixture of algebra and exponentials. So I'm going to come off to the side and I'm going to write my integration by parts again. So this time u is equal to x, which makes du dx. And the everything else part for dv is e to the 3x dx. So going backwards to find that antiderivative, my v is again 1/3 e to the 3x. This one requires being careful because that negative 2/3 is sitting there, and the integration by parts part I'm replacing the entire integral. So my entire integral gets replaced with, again, ultraviolet voodoo. So x times 1/3 e to the 3x minus the integral of 1/3 e to the 3x dx. Pause, simplify as much as we can before we do another integration. Although you don't have to do that step of the pause and simplify, if you, as these get a little bit more complicated, keeping track of minus signs is important. And so I just find that if I pause and simplify before doing another integral, it helps. So I've got that 1/3 x squared e to the 3x, and I'm going to distribute the negative 2/3 in to both pieces. So I'm going to have negative 2/3 times x times 1/3 times e to the 3x, or negative 2/9 x e to the 3x. Minus a minus is going to make that plus. I've got a 2/3 and a 1/3, so that'll be 2/9 e to the 3x dx. And finally, we've gotten down to an integral that I don't have to do u substitution on. I don't have to do integration by parts. We already know what this antiderivative is. I have unfortunately run out of space on my paper, so I'm just going to let you finish that off on your own. We're going to kick out another 1/3 here. Maybe I'll do, okay, so I can write it. Just write that part again. This is going to kick out another 1/3, so I'll have 2/27 e to the 3x plus a constant. Yeah, another excellent question in the chat. We know we get to stop on the integration by parts when we get to something that we just know how to integrate. So if I know how to integrate it, I get to be done, integrate it, move on with your life. Yeah.
Is it possible to use substitution in?
It is. So for example, here, if this wasn't obvious to you of how to get the antiderivative of e to the 3x, you could do like a mini u substitution and let u equal to 3x. We could also have something more complicated where I needed to do a u sub inside of a u substitute, inside of an integration by parts. I don't have time to finish this next problem, but let me just kind of put an example up of a place where it could happen. Let's say I walked up to this lovely integral and I asked myself, can I make it look like x's to powers? Nah, I got trig in there. So I'm hoping for the u substitution. And I look at that and I go, oh, hey, the derivative of x cubed is x squared. Calculus can never mess with what's inside of a trig function. I can't mess with the x squared. So I'm stuck with integration by parts. But I probably actually want to do a u substitution first. Because calculus can't mess with that x squared, I would probably start this by letting u be equal to x squared and making du 2x dx, which means that 1/2 du is equal to x dx. And then I'm going to look at this and say, oh, I need to translate everything in this problem into ASL. I got to translate all of it into our U substitution language. So I'm looking at this and going, okay, that part I know what to do with. That's sine of U. I don't really have a dx piece over here, but I do have an x times dx. So I'm going to borrow and I'm going to split up that x cubed to say x squared times x. This one and the dx together I can deal with, and the leftover x squared becomes u. So this would translate as, I'll kick my 1/2 out in front, but this really becomes u times sine of u du. So even after doing a u substitution, I am now forced to do integration by parts, because after the u substitution, I still have a mixture of algebra and trig. So I don't have time to finish this one off. I'm looking at the clock back there, but that's kind of an example. Some problems are going to require both u substitution and integration by parts.